Yeah, so I was going to say something about scalable raster data analysis in the cloud with R, and I will be trying to avoid the word big data, but data sizes are large, right? So, and I sort of intentionally asked Tom to put this talk after, let's say, after Tom's talk about how you can do these things with R, because this is kind of, I think it's very brave that you do this thing, and it's basically the only thing you can do now. Is kind of the whole sort of mess with tiling and parallelizing and chunking and putting chunks together. It is sort of it's a large effort to do things that way, and you can do it, but it takes a toll, and the thing is that you will manage, but there is a certain stage that you will no longer manage with certain amounts of data that you, let's say, on the machines that you're working on will no longer kind of work. And the question is kind of what kind of data sizes are we then talking about? But let's say very exciting data sets that are now coming down or that are now sort of freely available include, let's say, the Landsat 8 and Copernicus data, so the Sentinel-1, 2, 3, and 5 data sets, and they're sort of relatively large. And if you want to do analyses on these, let's say on continental scale, and do some kind of time series analysis of these type of data sets, then sort of the proposition to do these things, using the path that Tom laid out, is rather challenging for the simple reason that these data sets are so large. So it assumes really that first of all, the data sets you want to go through are on your local hard drive, right? And so doing that for continental Sentinel-2 data sets is a tough proposition. Yes? So the downloading of that data is sort of is problematic. So who of you works with data sets that do not fit on your local hard drive? Data sets the size, yeah? 2, 3, 4, 6, 7. Yeah, so that's quite a few people. How large are they? Who raised their hands? Give a number.
60 terabytes.
60 terabytes. 6 terabytes? Okay. 20 terabytes? Many terabytes. Yeah, good. Anyone more than? Yeah. Petabytes, right? Yes, petabyte. So, does any one of you do analysis that's distributed over more than one machine? Yeah, you do. Yeah, Grace. So that is another aspect, sort of the cluster aspect. And who of you thinks that this will happen to themselves over the next 5 years? One of these things. Yeah, so that's quite a few more than that. Yeah, so what we see is that, data sets get larger or sort of it gets easier to, well, one of the things is that one of the bottlenecks is sort of the speed with which satellites send information down, right? And they're optimizing that, they're optimizing sensors, the things become more open. The thing is that with large data sets, we don't only have this sort of challenge with raster data. Same thing is with large feature data sets. So if you think of, if you do a map view or something like that, you see immediately the backdrop, some kind of tiles on some zoom level, but let's say the whole tile set at the highest zoom level of the whole global sort of Google Maps or satellite backgrounds is a relatively large data set. You always see a little piece because you only download, let's say, the pixels of the little piece that you get to, and the services providing these are fast. But other things is OpenStreetMap backgrounds, you see these tiles, but if you would sort of serve these tiles and generate them from the complete OpenStreetMap data set, you can do that, but then you're looking at relatively large data set, and that's a static data set, right? That's not dynamic data like satellite imagery. PostGIS you can use, for instance, for larger data set. PostGIS seems to, at least PostgreSQL seems to work with clusters, so seems to be able to distribute data sets over more than one machine. What happens if if your data set is larger than a local drive, right? You have to think about this. Spark is sort of an analysis layer on top of Hadoop, I believe. GeoMesa is sort of a GIS layer that lives on top of Spark, or GeoTrellis does this for raster imagery, and so on. So there's a kind of infrastructure that works on that cloud stack is something what you can do. An issue if you have spatiotemporal data with features, if we have dense time series, so if we, for instance, have IoT data, we measure something every 5 microseconds for many locations, and we register that, so we get very long but also very dense time series for many stations. How are you going to store this data, right? So the naive thing from a GIS perspective would be to just replicate the feature, the location with every observation, but that's not going to give you easy time series analysis, right? I discussed that earlier in the context of data cubes in the stars package. Yeah? So the idea of data cubes really is not just a raster idea. It's an idea of sort of array layouts of things. Yeah? So we have vector data cubes. Vector data cubes would be collections of time series for different stations, as a simple example. So large raster data sets we have global digital elevation models of high resolution. They are static. They are, they get updated. We have global land use data sets. There is the climate model intercomparison programs. So these are sort of collections of climate model runs that are shared publicly that you can download, and there is sort of iterations of this program where the climate community discusses and agrees on scenarios to run for these big what is it called, for these big comparisons of climate reports. The CMIP6 they're now running these, I think, and the CMIP6 program is sort of planned to generate between 20 and 40 petabytes of data. Yeah, so that is the issue. Is then how much is 20 to 40 petabytes? Well, it's basically a data center, right? You need a data center. Here was a tweet that I always like these tweets about people sort of showing how large data sets are. This is one from Vito, where they say, well, this is what we had, 47 gigabytes. This is what we now have, 5 petabytes capacity. And of course, a lot of computing capacity, but it's basically a data center that you run, right, for a couple of petabytes. So you and I, or your research institute, or your university department or so, are relatively unlikely to do that. Yeah, so this needs a lot of investment to do. It needs a lot of manpower to administer, to set it up, to make it run, to administer it every day, to make sure it's available, and so on. And so the Vito group is an institute with 80, 90 people or something like that. Yeah, so it has a certain size, and they have a sort of turnover where this makes sense. And they also have a commitment to do the Proba-V satellites and so on. So they're a ground station for that, essentially. So that makes sense. And there are a couple of university research institutes, like the Patrick Hostert group at Humboldt in Berlin, and the Wolfgang Wagner group in Vienna in Germany, and the Verbesselt group in Wageningen, and so on, that build up, let's say, large image collections and do analysis with them, that where, as a PhD student, you can sort of start and work with these data, but otherwise, if you wouldn't do that, what do you do, right? So your PhD starts, you get a laptop, here you have a laptop, right? Now go and do something with the petabyte Sentinel-2 data. Yeah? And there you are, like, okay, what am I going to do? What is the sort of where do I start? So we have these sizes, we have the remote sensing data, Landsat, Sentinel, and so on. MODIS is relatively sort of nice and sort of smaller because it is much coarser resolution, and it's also heavily pre-processed also. That is kind of makes it so nice. It kind of comes as a data cube, and the other data sets don't really come as a data cube. So Landsat and Sentinel images come really as georeferenced tiles, but they are kind of image snapshots, one taken after another, right? It's the path of the satellite that you find in it. So it's like almost continuous in time. What the satellite does is, of course, continuous in time. It sends a strip, and these strips are then kind of cookie cut into rectangular tiles, and then you have these set of tiles. But it's not as if they come in a nice sort of three-dimensional or four-dimensional cube or something like that. Yeah, so you have to really work on that. In any case, with R, the only sort of production thing we have now is the raster stack in a raster package, which, as I mentioned earlier, has the concept of a set of layers, basically the original kind of static GIS concept. It doesn't really work for this, I claim, because we could sort of have a single image, single remote sensing image, as a raster stack with the bands in it, but then we have a time series of these images, and we have, let's say, a stack of stacks, right? So it is like, how are you going to interweave these things? So that you can do it, but it gets relatively messy. The good thing about raster, the very good thing that many people experience, is that raster is going to sort of not try to load everything from hard drive in memory, but it's going to do piece by piece, and it takes a long time, but it will finish. Whereas other packages, like if you would use SP, and it will read the whole thing in memory, and then you need to do these things with regdal, sort of do the tiling yourself, and then it gets sort of it gets relatively cumbersome to get things done. And the bottom line with raster and raster stacks with raster is basically that the data you want to go through is on your machine. Yes, that the data you downloaded the data first on the machine you're working on, and that is okay as long as that works. That means you have relatively small data, but not the data sets of tens, hundreds of terabytes or even petabytes. So how can we analyze these data sets without downloading them? Yeah, that is the thing. So looking at data is one thing, but analyzing data, like the things that Hannah did yesterday with a Sentinel image, so we could download this data set and we said, oh, it's Sentinel-2, but it was a little sort of piece of 1,000 by 1,000, so that's 1% of a single tile that we have, right? The tiles, Sentinel-2 tiles are 10,000 by 10,000, not 1,000 by 1,000. So that gives you an idea of sort of, it's a gigabyte, a single file is a gigabyte to download. So you're not going to do that in a class to work with. And if you do it sort of for yourself, for research, you can do it, but you can't do it with hundreds or thousands of these tiles or so in the downloading. So the question is like, what are petabytes and how can we work with them? What is sort of the network capacity problem? So if we download a lot, we often tend to think networks are fast. Like here, we think the Wi-Fi network is fast, right? But if we think about downloading a petabyte, it's not going to work. So it's never going to happen. Not in your lifetime or so, right? So it's kind of, we need to really do sort of other statistics or so. In many cases, data sizes at some stage, sort of the physically sending a bunch of hard drives somewhere to another place is a faster way of getting the data across than doing it over the internet. Yeah? So this is really sort of something that is not let's say a small factor. I don't have any numbers, but you pretty soon hit the limits of network capacities with when you want to download sort of very large data sets. And then the handling of imagery is kind of even more, let's say, cumbersome, because what you have to do is, first of all, store the tiles or put them somewhere on your hard drive. Then you need to index them. So indexing is kind of not a light thing. If you have 10 images, you could say, okay, put them somewhere. But if you have 100,000 or you have 1 million of them, which is not so problematic to get, then sort of which one is where, right? So you want to do sort of, at some stage, you want to do fast queries. So you need to think about organizing them in such a way that you can quickly sort of find out which ones are where. And that's all doable, of course. You would maybe have to mosaic them. That means that you have different sort of neighboring tiles that you put together in sort of a single coverage for a certain moment. You may have to harmonized tiles for different sensors. Yeah, so maybe you want to combine MODIS, Landsat 8 and Sentinel-2 and put them on top of each other. So that takes effort. That is kind of, you have the mismatch of all the grids and of the grid cell sizes and so on. You may have to run atmospheric correction models on some of these things. You may have to do cloud removal and so on. And these are kind of all things you basically would have to do before you can start with your research question. Yeah, because your research question will be using this data to answer a particular question, like what was the land use or how much deforestation happened in this region or something like that. Yeah. So before that, you have to do all these things, and the troublesome thing is that everyone has to do that. Yeah. So that makes it currently that there's a lot of research, remote sensing research happens in groups that already did these things. Yeah. That in groups where people prepared data, downloaded them, and sort of made this access easy and sort of made the data, so to speak, analysis ready. Analysis ready data is nowadays a word that, by the way, is used for particular ways. They're doing that with Landsat and so on, trying to make one sort of big composite of Landsat 8 for the United States, and that's very good. So that is the same for everyone. And so you would really like somebody else to do that for you, right? So you can focus on your research and using this data and train a model, calibrate a model, and predict a model or something like that, and generate a new layer out of that. On the other hand, you would also like to know how this works, sort of what these things, so have the details of how these things are happening and be able to control some of the details if you have to. So then, if you would do all this, then there is always the question, like, do I keep the files as they come, right? Do I keep them as the what are they, zip.safe.zip files, like the Sentinel-2 files come, they are zip files with like 100 files in them with a lot of JPEG 2000, or do I sort of unpack them and reprocess them and maybe put everything in a database? And if you would put things in a database, like talking about array databases, like whatever SciDB or Rasterman or something like that, if you would do that, then there is the question like, okay, I'm going to put them in a database. That means that I duplicate all the data. Am I going to discard then all the files? Yes, and keep everything in the database so that I don't duplicate my storage need. It matters in terms of costs if you need 3 petabytes or 6 petabytes. It's a factor 2, or do I leave the original files in place? And if I put them in the database, how about backupping the database, right? What if something goes wrong or so, right? Those are sort of all operational challenges that you're facing when you would do all this yourself. So then comes in Google Earth Engine. The Google Earth Engine is who of you was familiar with Google Earth Engine? Yeah, so I can maybe say a few words. I didn't sort of really prepare slides with it, but so it looks like this. It's a planetary scale platform for Earth science, data, and analysis, and it has essentially all the satellite imagery that we can think of that is freely available in it. In addition to that, a lot of other layers that are available, like elevation models or even classified derived satellite products, and you can pretty easily run programs in it. So you use your Google account. You first have to ask. They're asking you what are you using it for. So you have to say that I'm not a commercial company trying to make money out of your system, but I do it for whatever good scientific purposes, and then they're fine. And then you get access, and then you can do all kind of things with it, yeah, and fairly easily, right? So you get this interface where you have a lot of commands, and then you have here you write your JavaScript program that says do this with that layer, do that with that layer, and then here you get you click on the images sort of are processed, and you click on your pixels, and you see time series of what happens there for the material, for the things that you were looking at. And that is very good in many ways. Yes, it is extremely good if you're a graduate student who wants to work with massive Earth observation imagery, so time series for large areas, for instance, either large areas or time series or both, or just a small area and you don't want to go through the hoops of understanding HDF5 because somebody gives you a MODIS tile or so. And you can do that essentially after 1 day of training, right? So it's in that sense, they have a lot of examples and so on, good documentation. You can apply a lot of methods from computing indexes like NDVI or so to time series analysis to do machine learning and classification things. Very easy. You can sort of click your areas. The thing that Hannah showed yesterday is very easily done interactively. You do click, 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 click. Here's an area of water. Here's an area with forest. Here's an area urban, and you say random forest classifier, and zip, there your whole sort of thing trains and predicts, and you see how the results are. So there is it's very powerful in that sense. The nice thing is that we really can work with that system, with the data, as if they were data cubes, yeah? In the sense that you tend to, that it looks like, when you look like it at the system, it looks like all the data are in the same grid, because you look at the map and it shows MODIS, it shows Landsat, it shows Sentinel-2, everything. And you can say, well, do something for monthly data or so, do it some kind of time series for monthly average values or something, yeah? So that really sort of puts a spatial frame on stuff, that puts a temporal frame on stuff, irrespective how the original data are. And that is a sort of a very powerful concept, because the original data are not a data cube. As I said, maybe only MODIS counts as a data cube, but all the other satellite imagery are not data cubes. Yeah, they're sort of, you need to move them in time and so on, and put them together. If you put two tiles together, well, these tiles have different timestamps, yeah, because the satellite was at a different time there, right? So you need to sort of harmonize that in some way. So that is very nice. What is very good is that you basically, in an interactive way, you compute only the cells that you see. So as you see here, you do something, you see these cells, right? You think I'm looking at a continent, but you're looking at the continent at a 10-kilometer resolution, really, yes, because that is the size of a single pixel of your screen. And then it's going to update that, sort of run your model on that, and it means that it only computes the 10-kilometer resolution data. Yeah, so it thinks, oh, I have to run this model. Well, what are you looking at? So it's not going to run sort of the full resolution 10-meter thing on this continental scale, which would take like, a week or something like that on the single node, but it's going to do only the pixels that you see. So it's very lazy in that sense. You can do the full resolution, which takes a longer time and so on. But then you have to tell it. Yeah? So in interactive modeling, it's extremely fast and efficient, and it automatically parallelizes and things like that. So you can pick a temporal resolution to do things, and the regrading, downsampling, spatial and temporal really happens on the fly. Yes. What is not so trivial, what I think you can do, but working with datasets that are not in Google Earth Engine is sort of harder. You need to put them in your Google Big Tables, and if they are massive, sort of new imagery, so if you have like a new sensor or something like that, and you want to, or you have a petabyte datasets that you want to have imported in Google Earth Engine, then it might take a lot of resources to put that first in your own user space and integrate it, and so that is not trivial. I don't think it's impossible. Things you cannot do with Google Earth Engine is run arbitrary custom code on the imagery. So if I have my model is an an R support vector machine, or want to do some fancy, trying to think of something very fancy, but some kind of very fancy machine learning method that some R package provides, but that's not very mainstream or so, that you want to compare to a classifier that's available there, you can't run it there, right? So you're restricted to the API, the application programmer's interface, or the set of functions essentially that Google Earth Engine provides you. Yeah? So whenever you do you have your own custom code, you can't easily use it. They have a Python interface, and there is some talk that you can now integrate NumPy stuff and so on, but it's difficult because essentially you especially, or at least I know a lot more about R, but anyone can in R basically, program anything that God forbids essentially. Yeah? So they're not going to do that on their cloud, on their data, so to speak. So you don't want to sort of give complete control to anyone. You also can see the source code of Google Earth Engine, which probably has good reasons. One of the developers once explained to me that it's running on custom hardware with custom kind of operating system and custom programming languages that are developed for that hardware. So they could share it, but nobody could read it or run it, right? So what would be the sense of sharing all that, you would wonder, yeah? So this is kind of the thing of heterogeneity of systems, really. So it's hard to ensure reproducibility. On the other hand, with cloud processing, reproducibility is very difficult to get done in absolute terms. Or it's hard to get the guarantee that you get the capacity that you would like, right? So you can, of course, think of analyses that will run eternally. It will not be so hard. But you don't get infinite sort of compute power on the Earth Engine. And now Earth Engine doesn't have a thing like surface level agreement where you basically pay and say, I want that, right? So just give me so much uptime of so many nodes or something like that. So it doesn't have a pay model, yeah? That is because it was not set up for that reason. And now they don't have it, and it is difficult to backfit. So what do you do if you want to run sort of a global sort of model that takes 100,000 CPU hours? Yeah, Noel Gorelick will claim in talks that you can get it, but not everyone gets that. Yeah, so you may first have to explain why you want this and why this is a good thing that they want you to do this. Yeah? So fit arbitrary R Python models, use them to predict in the cloud is not something that you can easily do with Earth Engine. Alternatives to Earth Engine, well, there is the OpenGeoHub data hub coming up, but it is sort of looking into the stars a little bit about what it's doing. But anyway, we see a lot of sort of cloud-based processing environments for remote sensing data. There are sort of the ESA-funded or European Commission-funded thematic exploitation platforms. They are kind of 12 different ones for the 12 different themes. They all have different interfaces. There are the upcoming Copernicus Data Information Access Services, the DIAS. These are projects that are running now. So there was the Commission put, let's say, 25 million or so aside to have 5 of these systems up and running. And well, they might be up and running, and you might be able to do it. ESA also offers access to their cloud. If you are friendly, then you get a virtual machine, and you can sort of work on the data there and so on. But all these systems pretty much are different. If you would, if you want to start working in the cloud, then it's not sort of a couple of things are not entirely trivial in the sense that what is different in the cloud is that you quite often do not work with direct file systems, but you're rather working with object storage. It's called S3 for Amazon, Google Cloud Storage, document stores, object storage, and so on. And that is kind of a slightly different system to put large amounts of files somewhere on a system, yeah, and you can sort of read these things through particular protocols, but they're different protocols from, let's say, your typical open file protocol, right? So the standard thing you would do in C or even in R. So if you have like dedicated formats like HDF5 or NetCDF or SQLite, which is a database in a file, they need to do certain stuff that is sort of developed to optimize things. For instance, SQLite wants you to get a lock on a file, right? You open a file, you lock it because it's you're processing it, so you're the owner at that moment. HDF5 has also optimized a lot of things in their system, and these kind of systems compete really for the same smartness and gives some essential clashes. Yeah, so some of these formats do not work well in object storage. There is a thing called cloud optimized GeoTIFF that is a variety, sort of an iteration of GeoTIFF that was optimized for the cloud that works extremely well because you can do direct HTTP calls to a GeoTIFF and tell it with a range statement which part of the GeoTIFF you want to have. So you could make a GeoTIFF of 10 meters continent that will be many terabytes large, and you could do a single call that just reads this piece out of that file through an HTTP interface. Yeah? So that is extremely sort of cloud friendly. That is sort of how things do work, and all these other formats really also have to think. I saw recently I think on the GDAL dev list or so, there was some kind of talking about NetCDF also improving, trying to sort of get these things done with cloud storage. Yeah, because typically CMAP data, so the modeling communities write everything in NetCDF, which is the most, which is essentially the only proper format for raster data, and which has time as a variable in it. So GDAL or GeoTIFF and so on can't really deal with time very well. Other challenge is how do you distribute your computation over nodes? Question is whether users should know how to do this, right? Do you really sort of would like to work with a system that does that for you rather than think about how to do it and think about a strategy? And so ideally this would work out of the box. Other things you need to think about is, are my data close enough to my compute nodes? So Amazon Cloud is not just Amazon Cloud, right? So the Landsat 8 data sets are all in the Amazon Cloud in Ohio. Yeah? So if you want to sort of work with them, then you better rent a node that's in that data center, right? And not a node that's in Dublin, because that's not going to work very well. So if you have a node in Dublin and then read all the data from Ohio all the time you want to go through, that's going to be extremely slow and probably very expensive. Yeah? So you need to sort of move your computation also physically to the node where it is. And I think the Sentinel-2 data sets are in a node somewhere in Europe. So that will be sort of a nice challenge to make a system that combines these two data sets. That is data centers and compute nodes and where they are. And another thing is, where do I put is the file in my object storage, or is it on my local hard drive, the SSD? And if it's a GeoPackage file or so, an SQLite file, then you probably want to copy it first and then open it while it's on your SSD, rather than sort of open it from the cloud storage because of this problem that I mentioned earlier. So these are all challenges that a lot of data scientists really sort of would like to not have to deal with. Yeah, so it's just a couple of complications, and they're architectural, and they're sort of thought of to make clouds possible, yeah, to make sort of things with petabyte storage and so on work at all, because it's not going to work with file systems that we are using. This is technical reasons, but that's really not going to work. There is the stories about, I'm not going to say that. So now come OpenGeo.org. So OpenGeo is a project that started a bit less than a year ago, where I was kind of one of the principal architects. And OpenGeo is a project funded by the European Commission, which has around 8 partners or 10 partners or so. And what it does, it develops an open API, so an application programming interface, to connect R, Python, and JavaScript clients to big Earth observation cloud backends in a simple and unified way. This is the one-line summary that also the website says here at the bottom. And the website is sort of very, for an European Commission, for European funded project, very simplistic, but this is the best I could do. It's sort of, has a couple of things. What we did the first 6 months is prove that the concept works, right? So the idea is really this, that you, let me not just jump too much, yeah? So what is an API is the first important question. API, I said, is an application programmer interface, but what does that mean? It essentially is a language, yeah? It's a contract. It's a contract between 2 points communicating, right? So you could think of, the SF package and the SP package as giving you an API, yeah? It's a set of functions that you use to get things done, yeah? So you type in these functions, you click return, and something happens, yeah? So you're using that API. So that's basically all. So it's a language to do things. And what we try to do in OpenGeo is come up with a language where things that you and I use, R, Python, or maybe JavaScript to analyze data, to build systems, can talk to these backends. Yeah? So for some extent, this is already possible because the Google Earth Engine has a JavaScript and a Python interface. Yeah? So it has its own Java and Python API to work with Google Earth Engine. But that's only one backend that does that. And we expect that a lot of other backends or we see actually that a lot of other backends are being developed with a lot of funding, but with very little ambition of sort of working towards a single way of analyzing. And sort of our idea is that all of these backends will basically provide for a very large extent the same functionality, and that you could basically sort of wrap that up and define that, and define a language that can help you to carry out analyses. So in some sense, this is similar to providing packages that provide APIs for spatial data in R, or things, for instance, what dplyr and dbplyr do with scaling up your computations from R, from data frames to tables in big databases and so on. So that's also using a single API and sort of scaling that up to larger data. We have some sort of relatively large challenges in OpenEO. One of them is to provide user-defined functions in R, Python, or JavaScript that could be carried out at backends. Yeah, so what I said earlier is that I would like to run my dedicated self-programmed machine learning method, run that on these data, right, which are there, basically continental, Sentinel-2 over the whole Eurasian continent last 5 years or so. So that is something I would like to be able to do without knowing how this backend works. Yeah, so because it's, for instance, one Google Earth Engine will be one of these backends. I don't know how it works, but I also don't want to know. Yeah, so it should just do that what I want it to do. Or another backend which I understand how it works, but somebody else set it up and I want to run it there because there's other data that are more useful, or maybe it's faster or something like that. So doing that is a sort of a relatively large challenge, but we take that. Yeah. So there is a website that I just showed you, which is somewhat underwhelming, but there is let's say, if you want to look at results, then you can look at the proof of concept. The proof of concept explains what we do. We basically build an API. So there's this figure. So if we have like 3 clients, R, Python, and JavaScript, you would not like to have each of them develop an interface with 4 different backends, but rather use a single sort of language. The proof of concept included 3 use cases, which deliberately sort of were not extremely simple. The first one was quite simple. It says derive minimum NDVI measurements over pixel time series of Sentinel-2 imagery. So it involves computing an NDVI, dealing with time series, and doing an aggregate over a time series for every pixel. So pick the minimum NDVI value. The second one said create a monthly aggregated Sentinel-1 product from a custom Python script. So basically the UDF sort of challenge, set it up. And the third said compute time series of zonal statistics of Sentinel-2 imagery over user uploaded polygons. Yeah, so it has the raster polygon thing. You do something on raster data, and then for a certain area you want to say, well, this is the average, whatever, deforestation or something like that. So do a zonal statistic. So these were just 3 use cases, and we worked it out. And worked it out with a Python client, an R client, JavaScript client, and used these backends, GrassGIS, which is done by Mondialis, by Marcus, WCPS driver, so that is Rastaman, was done by Jurek, OpenShift driver was done by EODC, so that's Vienna, GeoPySpark, GeoTrellis was done by Vito, Sentinel Hub driver was done by Synergize, the sort of the company that sets up the Sentinel Hub in the Amazon cloud. Google Earth Engine backend is the Google Earth Engine, for which we developed sort of a front end and an OpenEO driver, and an R backend, which was just developed for testing purposes, so that you can also do something completely offline and locally on your own laptop and test this whole thing out. So these 7 backends were all sort of implemented with these 3 clients, and there are a lot of videos in which we basically show in a couple of minutes for each of them that things actually are working. And there is another, let me see if I can get this. There is this poster that some of you have seen at the EGU, where there is this picture of the JavaScript client here that Matthias Moore, a very bright student in my group, programmed, which is essentially just a JavaScript thing living in your browser that says, okay, here is an OpenGeo driver that I connect to, and here's a product I want to run, and here is kind of a process graph that I define, so that says, do some filter at date rate, compute an NDVI, take the minimum over time, and then show the data with stretched colors from where the stretch is from -1 to 1, and then show it. And he shows here this is an image, but this is interactive. Basically, you could press run, and then it runs actually in 2 different backends. And you can see here sort of move this little thing back and forth, and then on the left-hand side, you get the Sentinel Hub results, so that is computed in the Amazon cloud. On the right-hand side, you see the Google Earth Engine results computed in the Google cloud. And you see very different results for whatever reasons there were about scaling of the data, but it's simply a proof of concept that you can send an identical task to 2 different backends that both use the same data and should essentially produce the same result if everything was okay, when everything was not okay, but this is just to show that you can do it. And that is something that is sort of very, well, as a scientist or anyway as a data user, sort of should be very useful if you want to do, if you want to sort of process somewhere that the process you do sort of, that you get the same answer if you do it on another back-end engine, right? So you have an idea what's going on, which is not exactly the case here. You can see here all kind of things about job management and actions and jobs you can kill or not. And anyway, so the sort of the number of challenges that we're facing here are pretty large. We have to develop an API to access working systems rather than what we do is sort of in this sense ambitious, that we're not sort of trying to start off with all kind of existing standards like WP, Web Processing Service, Web Coverage Service, Web Coverage Processing Service, Catalog Web Service, OAuth 2, and so on. So we basically try top-down to make a working system and to define a language for that, rather than to use little building blocks that were developed to typically solve only a very small part of that problem. What we do really is build process graphs. Process graph is kind of the language that says this is the process I want you to execute, and it is nothing else than a nested expression call. Yeah? So in the end, if you have an R script, you break your script up in different expressions, but you can, of course, in the end, there's one result, and you can, of course, nest all these expressions, and you get your whole script back as a single function call, yeah? Which doesn't look nice, but this is kind of the thing, this is the program that you want to have pushed somewhere, right? So that is kind of the building block, the thing, the process graph is the thing that's going to be executed. We would like to have this evaluated lazily, like Google Earth Engine does, right? So don't compute more pixels, or only compute pixels the moment you ask for them. Yeah, so you want to see them, compute the ones you can see. If you want to download, only compute them for the area you want to download, maybe not for the whole Earth directly. And also you would, even more higher level ambitions are the ability to combine different OpenGeo backends. Yeah, so if I wanted to combine, for instance, Sentinel Hub with the soil or the vegetation data that OpenGeoHub provides, you would be able to do that. Then this is the example that I just showed you on the poster with the Sentinel Hub and Earth Engine. And irrespective of whether the data is stored as a data cube, what you would do is really provide a data cube view to users. Yeah? So this is one of the essential things that we also learned from the Earth Engine, that what they do is they don't create data cubes, they don't make mosaics at all. They just store all the data and some pyramids of it, but they store everything in their raw form, really. Maybe not in SJPEG 2000s, but basically not by moving of shifting pixels or something like that. So the pixels are there as they were observed. So the tiles are there. So the moment you mosaic things, you get things with, with boundaries that you may not want to do at some stage, or that you want to correct for or something like that. So doing that, or you would move things to another, you would regrid things and take a certain algorithm for that. So you might want to do that, but you can't force sort of a backend to do that. And essentially the original data there's just one form of the original data as you get them. Right? Until the moment you move or recompute pixels, you get different data, and sort of that propagates through everything you do. So, but the analysis view is always that of a data cube, right? You think of a mosaic and you think of some kind of time, sort of monthly data or 10-day data or something like that, right? So you want to do time series with time series in some kind of frequency. The nasty thing is that we also need to think of all kind of things that have to do with usability. So you have to think about user management. Who are you and what are your abilities to compute on this system? Where can users put data? How much data can they put? How much disk space do they have? Where do they retrieve data from? You have to think about cost management, because although Earth Engine is a free, typical cloud system, computing costs money, so laptops cost money. If you compute somewhere else, it also costs money. And a useful thing would be to have some kind of cost estimation, so that before you run out your complete credit on a script that contains a programming error, you would like to sort of get an idea what it costs to do certain things before you actually do it. So, but these are the more fancy things where we haven't sort of reached. Other aspects that turned out to be very challenging is that the discovery to discover and to describe data, and not so much to discover or describe individual tiles, because that has been done. I think of the Geos broker and so on. So you can find, tiles of Sentinel data, but if you want to describe, say, a product like Sentinel-2, how do you do that? So Earth Engine calls it S2, I think, and calls Landsat 8 L8, and that is very nice. But the kind of sort of what else do you use to describe image collections, really? Because that is the level that we think of these data, that we want to work with it, right? We want to work with band 3 and band 8 of Sentinel-2, or of Sentinel-2A, if you want to have one of the two satellites, right? And these are kind of abstractions of a very large amount of data sets, and there are some documents that say, well, this should, you should be able to search at that level, but nobody, funny enough, nobody has really sort of done this, and the way that Google has done this is sort of very spontaneous and not sort of not very rigorous. And if you do that, then the next thing is how you do drill down to bands, how are the bands described, and these kind of things, right? The band is then another sort of a sub-product is also an image collection. Another things that we at some stage will have to deal with is when you create a new product, maybe at the same resolution as Sentinel-2 or something like that, a global product, how are you going to publish that? Yes, how are you going to sort of make that available to others, and how can that be reused downstream? That is kind of how do you, which protocols, which names, which ways where do you put this information so that it can be found? So the project has, as I said, has started about a year ago, and next month we will have the first year meeting, and what we so far did was just a prototype. You can look at all the software that's on the GitHub page. There are a lot of sort of clients and backends developments and a lot of activity there. We just did a user requirement study, so this information is now being collected and sort of being compiled, and sort of will lead into the final requirements for the API. And the project is really thought as an open project, so anyone who's interested wants to sort of get involved, then please do come with questions and issues and find ways to contact us. Yeah? So we are a team, but this idea is only going to work if it finds users and if it finds adoption. So it's a little bit early for you. I tried yesterday to get this back end on my computer running and download data and get the front end and client and show you things where where one R session basically uses HTTP to communicate with another R session, and then sort of do these things back and forth with this little sort of, small version cloud. But I got stuck somewhere, and it's also very underwhelming to see that happens. But it's essentially the only way that this will scale up to real things. Yeah. So in parallel, and what we also use is this stars package, sort of the methods and the way it can apply functions to dimensions like to time or to band or to XY space, and the abstractions of it, because it essentially represents sort of, it's an R structure to represent vector and raster data cubes, which are kind of also the sort of the mental building blocks of the whole OpenEO approach. So we will be using that on both sides of the R, probably on the R client side and on the R backend side. So are there any questions from your side? So a few people asked me this week, like, what are you doing for research? And this is taking a lot of my time. So it's a lot, it sounds a little bit like computer science, but I think it's enabling, right? So this is kind of making things that in a couple of years might make it much easier to work with with raster data that are sort of not on your machine, essentially, right? Because they're not going to live on your machine. A lot of this data is not going to work to live on your machine. And it's too hard right now. So are there any questions, Tom?
Yeah, so this OpenEO, I mean, what is really going to change in 2 years? I mean, what's the milestone that you want to achieve?
Well, we will have a stable API. So that is an API that is flexible and thought through and powerful, and hopefully a number of good implementations. Yeah, so we have a very good team on board, as you can see from the project website, who sort of groups that already work with backends and that have to worry like, okay, but how are my users going to use this? Yeah, and this is a way that users can potentially are going to use this. Yeah, so and hopefully more than only the backends, the partners in this consortia will think this is a good idea and say, hey, I can see this advantage of also doing this because it gives users the flexibility to choose, okay, I can do my computation here, I can do it there, or I can do it there. Well, let's compare. What's the price difference? Let's ask the price for this job. Yes, oh, here are 3 prices. Okay, I go with that one, right? So these kind of things are now unthinkable, yeah? You first have to spend a month or so with one backend before you find out what your computation is going to cost. A month, yes, instead of seconds. Yeah, so that is one of it will sort of help a market, I think. Yeah, but it's, of course, that is assuming that it's going to work and it's going to be adopted, which we are not guaranteed.
So these guys from Conservancy International, they made a plugin for QGIS, and this plugin you need to have a Google Earth Engine account, and you enter that account and you can go from Google Earth Engine, from QGIS, and you can send things, you don't even have to log into the Google Earth Engine page, and you can send things to your computer and return in the R.
So it will log in.
Sorry?
It will log in. It will log in for you.
Okay.
Yeah, that is how Google Earth Engine will not work without authentication. But authentication can be automated.
I think at this stage of big raster, I think the first problem that most people have isn't processing the data; it's actually getting your hands on it. Mm-hmm. And I think the point that you made about it's impossible to download some of the huge tiles. So if Google Earth Engine or whatever can break it down, that's like the most useful thing for most people at the moment. And I just had a look on the WorldPop website, and they've got a raster pixel data set of all the world where you can just draw a boundary, an arbitrary polygon in their web user interface and download it. And that was really good. I tried Google Earth Engine, and it seems like they like you apply to join and then they're like, oh, well, we'll let you know when you're ready to join and download data. So there's a data access control. So I guess the question is, how will it help easily download data, and will other organisations like WorldCop be able to use OpenGeo to help make their data more available through an API?
Yeah, I think that downloading is just one thing that you can do, that you also can do on Google Earth Engine. You can do it anywhere, but it's not and there are a lot of standards that are good for download, right? Web Coverage Service is a download service. So I don't think that downloading is so much of a problem, or creating access services that can do it, for which there are useful clients that can work with it. But I think the downloading sort of will go out of fashion.
Downloading like a specific region can be quite useful.
Yeah, you can do that. You can do that with WCS. You can say this coverage and then that region, that bounding box.
About computation.
Yeah. Downloading is not technically not such a problem right now. This is the sort of the problem we are looking at is where you want to analyze data that are not too large to download. Yeah. Okay, any other questions? Then if not, thanks for your attention.